All right, this is Chris back again with the Ancient Scholar, and now we're going to go ahead and take the Michaelis Menton plot that we did in the last video, and we will do another plot that is going to provide us some information that will help us in what I'm going to be talking about, at least. It'll help us understand what's going on with competitive and non-competitive enzyme inhibitors. So with that in mind, this is just a recap of, let's see if I can go back here, of the Michaelis Menton plot that we did in the last video here. Okay, so here I have my Michaelis Menton plot, and just some of the important things. This is the velocity of the reaction, as a velocity of the reaction as a function of the molar concentration of substrates. And this is a fairly typical plot where as the concentration increases, the velocity increases until I have enzyme saturation, at which point it doesn't matter how high the concentration goes, I won't see an increase in the velocity. That line is called the Vmax. And then we find 1/2 Vmax, so that's about half of the maximum velocity. Follow that over, drop a line down, and whatever concentration that is Km, and Km is just the Michaelis constant. And the Km, as we talked about in the last video, and I'll just go back there, is a way of talking about enzyme substrate affinity, and that is to say that there is an inverse relationship between the Km values and the enzyme substrate affinity. The higher the Km, the lower the affinity; the lower the Km, and the higher the affinity. Okay. So there is another way of looking at this, and this is perhaps not as intuitive, so I'll kind of take it slow. And I don't know if you guys have noticed this or not, but I have taken it a bit slow in these videos, and I'm probably going to get a number of dislikes on my videos simply because they are so slow and take a long time to build up. I think if you really want short, bite-size videos, there are plenty of shorter, more well-structured, if you will, videos that are more based on high yield and just kind of little sound bites. They're wonderful videos, absolutely wonderful videos when you don't have the time to watch 300 hours of buildup. So I would definitely encourage you to check some of those videos out, because they're out there, and they are absolutely wonderful videos. I've actually watched some of them as I have struggled to learn this, but the videos that I'm doing are more slower paced build-up kind of videos. So that is what it is. Okay, so what we're going to do is we are going to use the same information here, but we're going to plot it a little differently. And what we're going to do is we are going to take, and maybe I'll just change the colors here, we are going to take the reciprocal of all the values. Okay, so the reciprocal. All right. And what in the heck does that really mean? Well, a reciprocal, so let's say that my molar concentration is, 1 mole per liter. What I do with the reciprocal is I turn this into whatever I'm looking at into a fraction, basically. Okay, and what I do is, let's just say that I have a concentration of, I don't know, 5 units, whatever. And instead of charting it as, or instead of documenting it as 5 actual units or whatever we're measuring, what we will do is we will take 1 divided by the value. 1 divided by whatever the value is, okay? And the same thing happens with the Vmax. Instead of the actual velocity, I will do 1 divided by the velocity. That's what it means to take reciprocal, is I divide, 1 gets divided by whatever the value is that I'm looking at. And that's really the easiest way of thinking about the reciprocal. So what this does is this markedly changes the way that the graph at the end of the day looks. So what I'm going to do is, I'll use a different color, is I am going to take the reciprocal of this, okay? And that's going to change things a little bit. So what's going to happen is oh boy, that was way off there, wasn't it? I'm going to go ahead and draw another graph here. So here is my x-axis, and here is my y-axis. Okay, now what I've done is, this is the same thing as this. This is 0, just as 0 is here, but I've kind of extended this out here, and that's what you see right here. In this graph, having negative values, something less than 0, it doesn't mean anything here, but it is definitely meaningful on this reciprocal plot. Okay, so let's talk about the x-axis here. So the x-axis here is the actual molar concentration, okay? The x-axis here, okay, is going to be a little different. And what it is it is simply going to be 1 divided by the molar concentration of substrate, okay? So 1 divided by the concentration. And then here, so the y-axis up here is the actual velocity of the chemical reaction, whereas the y-axis here is simply 1 divided by, I guess I don't really need to put brackets there, that's probably confusing, 1 divided by the velocity here. All right, so now what's going to happen is this line here is, a couple things going to happen. First of all, this line here is going to become straight, and it'll often start back here. All right, so what's going to happen is the line might look something like this. There we go. Well, I guess that's not terrible. God, it's kind of bent though, isn't it? I don't know why that bugs me, but it kind of bugs me. And you know what's going to happen is it's going to look even worse now. Okay, whatever. All right, so there we go. So this is the this line here. I have now charted this in reciprocal format. So there are a couple of important things we want to know here. The first thing is that where this line crosses the x-axis down here, okay, so wherever I cross the x-axis, all right, wherever I cross the x-axis, okay, that is actually going to represent the Km value. Okay, that is a way of looking at the Km value. Well, that's pretty handy. Okay, so where this crosses the x-axis, that's going to be my Km value there. Okay, and then the y-intercept right here. Okay, so where this crosses the y-axis, so the y-intercept right here, that is going to be indicative of my Vmax. Now obviously these are 1 over Km and Vmax, but they're still just another way of looking at the Vmax. All right. Now, because this is an inverse plot, this is a little weird. We should be aware that as I go up on the y-axis, that is going to be an increase Vmax. Okay, fair enough, right? Going up, increase Vmax. Totally got that. That makes some sense. Or I'm sorry, no. What am I saying? Look at that. I'm confusing myself. I am confusing myself. Excuse me. That's why we got to be careful about this reciprocal stuff. Okay, let's say that again. As I go up on the y-axis, because this is all reciprocal now, it's 1 over, as this point goes up on the axis, that is going to indicate a decrease in the Vmax. All right. As I go down toward the x-axis, that is going to be indicative of an increase in the Vmax. All right. All right, and likewise back here, I'll do this in a different color. Back here, as this point moves to the right, okay? So as this moves to the right, this will indicate, so let me just draw that here. So as I move this way, that is going to be indicative of an increase in the Km, all right? Because this point, as it moves to the right, is getting closer to 0, because these are negative numbers back here. So if this is, say, -3, and I move over to -2, well, -2 is larger than -3. So as this point moves to the right, my Km value is increasing. And likewise, as this point moves back here to the left, that is going to be indicative of a decrease in the Km value. So this plot here, we collectively call this guy the Lineweaver Burk, the Lineweaver Burk plot. All right, and the Lineweaver Burk plot is simply the Michaelis Menton plot in recharted, if you will, in a 1 over or in a reciprocal format. Now, this Lineweaver Burk plot, as unintuitive as it may seem, is nice because it can help us identify very quickly and easily what is happening to my Vmax. Is it going up and down? And my Km value, is it going up or down? And that allows us to, when we chart this way, that allows us to quickly and easily identify what's happening to my enzymes, what kind of, in the case that I'll talk about in the next video, what kind of enzyme inhibition is occurring. Is there a non-competitive inhibition, or is there a direct or competitive inhibition occurring? And how can we see that by appreciating the Lineweaver Burk plot? Okay guys, I'm going to go ahead and cut it off here. Hopefully this is making sense, and hopefully you're finding this interesting and helpful. As always, thanks for hanging in there.